Hey everyone, today we're going to talk about uncertainty in measurement, which is our third lesson in the first unit here. And basically uncertainty in measurement has to do with, number one, significant figures, which is one of your favorite topics, and also how we get uncertainty in different measurements, how certain place values in a measured value or measured number aren't necessarily very precise. They're oftentimes estimated, and that's usually the last digit that we have in any number. So most numbers are going to come from some type of measuring device that actually obtained the number. And most of these digits are going to have a certain level of precision to them, which is resulting from the device that we're using. But we're always going to have usually one digit that's going to be estimated and therefore is not very precise, which means pretty much every measurement is going to have some type of uncertainty to it. The uncertainty can result from quality and limitations of the instrument itself. How good is the person at reading the device? And a lot of things can go along with that as well, or their knowledge of using the instrument, as well as the number of measurements made. Now, when we did our Barbie doll bungee jumping lab, we did several trials and we made several measurements as to hopefully reduce some of this experimental uncertainty. And by using repeated measurements, we can really help to offset that uncertainty. So if several measurements are taken of the same event, let's say you're shooting baskets, shooting free throws, and you're going to do 100 of them, and you keep hitting the same spot on the backboard every single time. So every shot's nearly identical. These measurements are said to be precise. Now, if those shots kept hitting directly in the middle of the square of the backboard and going right into the basket, or going even better, swooshing right through the basket every single time, which is the accepted value of the basket, or if you're shooting on a target and you're hitting the bullseye every single time, those shots are said to be accurate. So precise measurements are repeated measurements that are close together. Accurate measurements are close to an accepted value or target. And of course, we'll give you an example here. The acceleration, or the accepted value for the acceleration due to gravity, which is near the Earth's surface and will change as we move farther away, but near the Earth's surface is 9.81 meters per second squared. And if a student who's doing an experiment to see if this is actually the value measures 9.98, and 9.99 meters per second, are the measurements precise, accurate, or both? Feel free to pause this video and answer this question. They would be precise only. The measurements are within 1/100th of each other, but they are still almost 2/10ths away from the accepted value of 9.81 meters per second squared. Now, a little bit of a review on significant figures. If a measured value, or in a measured value, the digits that are known with certainty are known as significant figures. We'll also include in that one digit whose value is estimated. So we go beyond, or usually one place value beyond the precision of our measurement, which that is actually estimated and has some uncertainty in it. These can also be called significant digits. That means the same thing. The greater the number of significant digits we have, the greater the accuracy of the measurement. Non-zero digits in a measurement are always significant, 1 through 9. Any zeros appearing in a measurement may or may not be significant. It depends on the following rules. If a 0 appears before a non-zero digit, they are not significant. If the zeros appear between non-digit numbers are sandwiched in between, they are considered significant. Now, zeros that are going to appear after a non-zero digit, or towards the end of a number, are going to have to satisfy one of two requirements. They have to be followed by a decimal point, or they have to appear to the right of or after the decimal. And we'll look at a few examples of exactly what this means. So first example here is 0.04. We have zeros that appear, I'll write this on the side here. This has to do with rule number 1. Zeros that appear before a non-zero digit are not significant. So in this case, only the 4 is significant. We have one significant digit. For the second one, this is also following rule number 1. Zeros appearing before a non-zero digit are not significant, so the last two are significant. Feel free to pause this and attempt these before you actually see how to do these if you'd like to get more of the benefit of the practice. The third one we have the second rule. Zeros that appear between non-zero digits are significant, so they're sandwiched there, so all 5 of these count. 5,610 kilometers. For this one, we have zeros that appear after a non-zero digit, but those ones are not followed by a decimal point. So we are not going to count that 0, and we'll count the 3 and 5, 6, 1 of 5,610. Number 5, this also deals with rule number 3. We have a 0 that appears after a non-zero digit, but it is to the right of the decimal, so therefore it is significant. So we have 5 significant figures. In 450 meters, we have a 0 that appears after a non-zero digit, so that's rule 3. We won't count that one at the end because it's missing the decimal, therefore we have 2. For number 7, 18.0 grams. This would also be rule number 3, and that 0 appears to the right of the decimal. So all 3 of these would be significant. Number 8, this follows rule number 1. Zeros appearing before a non-zero digit, so the 7, the 0, and the 5 would count. That 0 in the middle there is sandwiched, so we do include that. 650 point moles. This would be rule number 3. The decimal point comes after that 0, so we do count that. So we do have 3 significant figures there. And the last one deals with rule number 1. Zeros appearing before a non-zero digit. And this is also number 3. We would include the zeros at the end for a total of 4. Remember, we have 2 different rules here for when we are performing different operations using significant figures. And in general, we want to perform a calculation and then round to sig figs. We don't want to wait till the end. After each operation, we should be rounding and then moving on to the next operation. So we're talking about adding and subtracting with measured values. As long as they're expressed in the same units, we can combine them. The sum or difference is rounded to the same decimal place value as the least sensitive measurement. Whichever number has the fewest number of decimal places or the lowest place value, that's what we're going to round our answer to. So when we go through and add up in the first example here, we add up these values, we get 48.405. 0.5 centimeters. The least precise value in the original numbers, I wanted a highlighter there, is the tenths place here. So therefore, we're going to round ours to the tenths place. So this will round to 48.4, and don't forget your label, your units, which are centimeters. Example number 2, we add these together, we end up with 38.417 meters. Our least precise or least sensitive measurement ends in the tenths place, so we're also going to round to the tenths place. This becomes 38.4 meters. In the last example here, adding each of these up, we get a total value of 141.890 kilometers. Again, each number has the same units. The least sensitive measurement was the 7 in the ones place. So we're going to round to the ones place, and we get 142 kilometers. Rules for multiplication and division are a little bit different. When multiplying or dividing measured values, we perform the operation, and it's going to be rounded to the same number of sig figs as appears in the value that has the lowest number of sig figs. And we'll do 2 examples to see exactly what we mean by this. So if we divide 380.0 meters by 3.8 meters, we get an unrounded answer of 1,444 meters. Rounding that, our 2 numbers here, this one has 2 sig figs, 3.8, 380.0 has, 4 sig figs. So our answer should only have 2, which means they're going to be these first 2 values here. So we're going to round off the last 2 place values, and this is going to round to 1,400 meters. We have our 2 sig figs there, the 1 and the 4. For the last one here, if we divide 56.2 kilograms by 6.003 kilograms, we end up with a value of 9.36198 kilograms. 56.2 has 3 sig figs. 6.003 has 4 sig figs. 3 is the lower number, so our answer should only have 3. And when we round this off, we end up with 9.36 kilograms. We'll do lots of practice with this in class. I'll leave you today with a joke. If you've ever heard any jokes in physics, the frequency of bad physics jokes hurts. Enjoy your weekend, everyone.